Hi, I am not Major Grant Thomas, whom you are used to. I am Major Cameron Cunningham. I am the poor man's Grant Thomas. I work at the USAFA Astro Department. You may have seen me before, or heard me before at least. You've seen my hands in my tutorial videos, but today I actually get to step in front of the camera and chat with you about command and data handling subsystems and telemetry tracking and control subsystems on satellites. So with that said, let's kick this off. All right, so the lesson objectives that we want to chat about today are kind of twofold, and I would group them into command and data handling and telemetry tracking and control. So understanding the concept behind and calculating signal-to-noise ratio. So that's going to involve signal strength. Basically, and you have experienced this before with your cell phone, if you've been trying to get service somewhere where your phone is not strong enough to reach the nearest tower. We're going to talk a little bit about that. We're also going to talk about the command and data handling part, which is depending, and again, this is kind of a daily life application just as much as a satellite application. But if you wanted to send a huge high-resolution picture to your friends, again, over the cell phone network, you might have the little blue bar that goes across, if you've got an iPhone or an Android, and it says, I'm sending picture in progress, and then just hangs because it's trying to pump a lot of data through a little pipe. We're going to talk about that calculus as well. Okay. Telemetry tracking and control subsystems. So I'm a space operator by trade. This is one of the most important things to me because it allows me to communicate from the ground up to my satellite. A way of thinking about it is that telemetry tracking and control subsystem is the ears and mouth of the satellite, right? So ears to listen to commands and information from the ground, and mouth to pute back data back down to the ground, especially whether that data is satellite health data or other kinds of data. We're going to talk about that in a second. But I love this little image. This little graphic is from the book. And it basically shows the subsystems and payloads that are on the satellite get filtered and packaged into usable data, rather broadcastable data, and sent out through the antenna and broadcast system of the satellite all the way down to the ground. I want to talk about the kinds of data that we receive from the ground if we're a satellite, or if you're an operator like I am and was, the kind of things that you get back down from the satellite just in terms of data. The first type of data that we have are commands. Those are literally software commands that operators type in or click or select, and basically they're telling the satellite to do a thing. Right, so that could be turn on this particular subsystem, tilt the solar panels, turn off a battery, turn on a battery, turn on the thrusters, turn on the attitude control system to tilt the satellite. I mean, you imagine it, and that's the limit. Your imagination is the limit for what commands can be. Same thing with a computer that you have down on the ground. Each of your mouse inputs to open up a program, that's a command. So we have the same thing with a satellite. It's just that instead of your keyboard being hooked up, just to your computer, it's hooked up to a computer that sends commands thousands of kilometers away sometimes. So those are what commands are. Commands are what they mean. Telemetry is a specific word that means health information, if you will, that comes back down from the satellite. It's actually kind of used in a way that collects all the information from the satellite. So for example, battery voltages, temperatures, pointing information about where the satellite's pointed, amounts of fuel that are left. It's a tough thing to judge, but all of those information bits are part of the concept of telemetry. They're talking about the health and status of the satellite. So that is one important thing that operators want to get back down from the satellite. That is just an important, very important thing because it allows us to track, is our satellite in trouble? Is it doing okay? So we are very watchful about our telemetry. Okay, the last thing is the mission data. So that's just another form of data, but it's not telemetry. It's not about the satellite itself. Mission data is what your satellite was launched to do in the first place. So mission data for a photography satellite, for an Earth remote sensing satellite, would be images. That would be the mission data. They're sending back the images that they took. For GPS, for example, the mission data is position, navigation, and timing information. It's what we launched the satellite to do, is to broadcast that information. Or finally, for like a communication satellite, taking users' phone calls and texts and internet and packaging it up and relaying it, that would count as mission data for a communication satellite. Or rather, mission data for a communication satellite. Okay, this is where we're going to make our money in the TT&C part of this lecture. We're going to talk about the signal-to-noise equation. Okay, basically, what this is talking about is a ratio between the signal strength of the signal you're trying to send to your satellite and the background noise, RF noise, radio frequency noise, that the satellite is picking up. And the analogy to your friend in a crowded room is how I always describe this. If you are in, for example, a very quiet environment, like you're sitting at church or you're sitting in a briefing where everybody is quiet and there's only one speaker, the speaker doesn't even have to speak that loud for you to pick up what they're saying with your ears. However, by contrast, if you're in a crowded room where everyone's talking, first of all, people will start to talk louder and louder. That's kind of a human tendency. So that, and because of the fact that they can't hear each other unless they try and get the strength of their signal, which is their voice, up above the background noise of the murmurs in the room. So if you try and shout at your friend across the room in a crowded room, he probably won't be able to hear you because your voice isn't strong enough to stand out against the background noise. So your S isn't strong enough to beat the N. So what I mean by all this is we want signal-to-noise ratios of bigger than 1. Because what would that mean? Well, it would mean that the signal strength on top is stronger, or bigger, we'll say bigger, than the noise strength on the bottom there. Or put another way, if the noise was bigger than the signal strength, this would be a fraction. Signal to noise would be how do I put this? It would be less than 1. It already is a fraction, but it would be less than 1. We want it to be much, much greater than 1 if possible. So what kind of things drive that? Well, the power of the transmitter, so in this analogy, the power of your voice trying to shout to your friend, the gain of the transmitter, if you imagine yelling through a megaphone versus just yelling omnidirectionally, your voice goes mostly just kind of out in a sphere or a half sphere. But if you focus it with a megaphone, that actually helps your friend hear you against the background. So that's what we call gain. Gain is a concept that talks about both the shape and size of your dish, of your antenna, and its ability to focus your signal in the direction that you want to go. Let's see. Lambda. This symbol right here, you guys are actually used to, I'm sure, from physics. It's lambda, and it describes the wavelength of a particular signal. And so higher, bigger wavelengths have an easier time, or put it this way, to the power of squared, they actually have an easier time penetrating background noise, according to this equation. And the last term on the top is the gain of the receiver. So if you had, I don't know if you've ever seen movies where someone's trying to listen to something that's happening in the room next door, and the door is locked, so they put up like a cup right to the wall to try and hear what's going on. The cup helps focus the audio energy that is being vibrated off the wall. That's a similar thing. So in our crowded room analogy, you're trying to shout to your friend and he can't hear you, so you use your megaphone that focuses your voice and assume that he has somehow an ability to grow huge ears. All of a sudden, that would help focus your signal even more so that he could hear you. So basically, the gain of the transmitter and the gain of the receiver in the actual satellite context have to do with the size and shape of the transmitting antenna and receiving antenna. All right, so then on the bottom there, on the noise term, because you could think about this, everything up top as the signal properties and everything below as noise, or things that would contradict or fight against you to get your signal. So on the bottom we have K. K is a constant. It's a Boltzmann's constant. And let's see, B is bandwidth. Bandwidth, receiving system's bandwidth. So bandwidth is essentially how big of a chunk of the electromagnetic spectrum are you using to send signals. So it's not the same as the frequency of the signal. That's a property that's wrapped up and directly related to wavelength, which we already talked about. Bandwidth instead is, for example, you could say, so for example, voice signals when they're transmitted over digitally are a 44 kilohertz bandwidth signal. They generally occupy 44 kilohertz of bandwidth. Now that could be from 1 kilohertz up to 44 kilohertz, or 1 to up to 45. It could be 50 up to 94. Where the chunk shifts in the spectrum doesn't matter. Bandwidth is just how big the chunk is. So for example, like we're talking about voice signals, take up 44 kilohertz worth of the spectrum wherever that shifts. Let's see, 4 4 is a constant, pi is a constant. R is essentially not, and this is an important fact, this is not the same R that you are used to from the rest of Core Astro. This R is talking about the distance between the transmitter and the receiver. So it doesn't have anything to do with the distance from the center of the Earth up to your satellite. That's how you've been thinking about R, and that's been correct so far. With this equation, it doesn't mean that. R is just the distance. It's a position distance magnitude between the satellite and the receiver on the ground. Okay, and I have some slides to show you in a second about that. Last thing is temperature. Believe it or not, temperature actually plays a big role in how well we can receive a signal. Hot antennas don't receive or transmit signals as well. Really weird, right? But because the term is in the bottom of the equation, bigger temperatures or hotter temperatures mean worse signal to noise ratio, lower signal to noise. So you would like to have, in an ideal world, you want lots of power, big antennas, low wavelengths, as little a bandwidth as you can, because the more bandwidth you take, the bigger amount of spectrum you have to compete against. So bandwidth is actually a noise term, in that bigger bandwidths struggle more with background noise to transmit. And then, of course, position. We would like to have the transmitter and the receiver be right next to each other. We want to minimize R, and we want the antenna and transmitter and receiver to be cold, right? We would want low temperatures. In an ideal world, that's exactly what we would do. But of course, we don't have an ideal world. Let's chat a little bit about range. Okay, so I just want to give you a scenario. When a satellite rises up above the horizon, we literally call it rise, satellite rise. It is as if it's another planet or star or the moon, right? You can have moonrise and you can have sunrise. You can have moonset, but more commonly sunset. So the minute the satellite, if our satellite is traveling from the right side of the screen to the left side of the screen along the direction of my mouse here, like this, the satellite will first peek its head, if you will, up above the horizon right here. That'll be the first time that this antenna can actually have a chance at communicating with the satellite, because before that it is below the horizon and the satellite cannot send or receive a signal that penetrates the Earth, the mass of the Earth. So this instant in time where the satellite first pops its head up above the horizon, we call R max. It's the worst case distance between between ground station and satellite, between transmitter and receiver. This is because as the satellite continues along its path, its distance between itself and the ground station decreases. As you recall, a smaller distance between helps us get a better signal, until the point where it's directly overhead. And this is what we call R min. At R min, the distance between the transmitter and the receiver, or the satellite and the ground station, is as small as it's ever going to be. When it's directly overhead, it's as small as it could possibly be. And in that case, the distance between transmitter and receiver is just the h, or altitude of the satellite above the ground. Here are a few things that you could do to help your signal be better. You could talk louder. Again, we talked about the megaphone, right? Increasing gain. You could get closer. Space loss is that squared term in the equation. Basically, the amount of energy bleed off just by virtue of a signal traveling through space. That's technically called FSL, free space loss. Listening with bigger ears, we talked about that. If your buddy across the room could somehow grow bigger ears, he could hear you all the better to hear you with, right? He could hear you more easily. You could talk slower, something I sometimes struggle with. But that has similar to do with the bandwidth. Not quite the same as the data rate, but that's a whole class unto itself. If there's a way you could reduce noise, that would sure be nice. I would say that's the thing that you have the least control over in the world. Is you can't just kick all the people out of the crowded room. They're there, and you sort of have to just deal with it. So those are things we could do to make a better signal. Okay, so that's all I really want to say about the telemetry tracking and commanding subsystem. And we spoke mostly about, the range between transmitter and receiver, and of course also the signal-to-noise equation and all the things that govern it. That matters a lot for we operators who are trying to communicate with the satellite. Now let's talk about the command and data handling subsystem, or the CDHS. Some of the things that we think about with data handling are, if your satellite, and we're going to focus on imagery satellites because they have very specific needs as regards data storage on the satellite. Communication satellites don't generally have this. They just rebroadcast the signals that are coming into them. GPS does not have this issue. It's not storing data. It's literally broadcasting data from its onboard clock. But imagery satellites, Earth sensing, remote sensing satellites, and, other satellites around other planets have the same issue, because often they have to take pictures on a different side of the Earth than the ground station that they use to talk to. So that means that you have a time where you've taken several images of a part of the Earth, and you have to wait, you the satellite have to wait until you're over a ground station to download all those. And then the risk is that you don't actually have enough time to download all the images. So a couple of things really matter. How big the image is that you take, like how many bits are in each image, how big the hard drive is that you have on the satellite that you can store, and then when you're over a ground station, how fast can you get the data down, or are you going to not have enough time to basically get all those images down? You guys have the same issue when it comes to, we all do, when we use the internet. I remember back in the days where you were downloading something from the internet at 56 kilobits per second at the upper end, and there'd be a little image on Windows at least of a file flying across the screen, and then another file flying across the screen, and it would say 3 days until download is complete. For a satellite, that's not going to fly, right? If I have a bunch of images to download, I want to maximize my data transmission. So that's what we're going to chat about here. The command and data handling subsystem is truly the satellite's brains. That's a good way of thinking about it. It has a CPU, or a central processing unit, just like your computer does at home, and it's got lots of I/O, which is input-output ability to send and receive information. So basically, this CDHS works hand in hand with the TT&C, right? So receiving information from the ground, it decodes that information and disperses it to onboard satellite systems. And then the other way, especially when this, for example, like I talked about, when the operator is asking for telemetry, all that information gets collected by the CDHS, packaged up into one stream to send down to the operator. So the CDHS is essentially wedded at the hip, attached to the hip to the TT&C. Some of the things that, if you're a CDHS, you have to worry about are collecting, as I said, signals from the whole satellite and putting them into a human-readable form, or at least a form that can be transmitted in. Interfacing between all the different components is surprisingly tough. You want to make sure that the data coming out of the satellite doesn't have to be decoded excessively by ground operators. It'd be nice if it was packaged up in a way that we could quickly read and use. And then data storage, like we talked about. In particular for imagery satellites, this is a big deal because of the calculus we talked about. Are we going to run out of space for the images that we're taking before we can get rid of them? And then, of course, processing. The more processing you can do on board, the more helpful it is for your ground operators. However, it also adds cost and complexity. The old trade-off between cost and complexity. So this is a kind of a great example I like. If you have an image, for example, we'll just talk about image quality, that only uses 1-bit pixels, the image on the left is the best that you can get. So the image on the left, you can tell. I mean, they're all black and white, but as they move to the right of the screen, as those, you use a 4-bit per pixel and then an 8-bit per pixel, the image quality gets so much better, right? But then the size of each image gets bigger. So imagine, if you will, that you are a satellite such as Worldview 3, which is pictured here, that is one of Digital Globe's. We're not doing advertising for them, but for example, Google Earth buys a lot of their imagery from Digital Globe, and they have these imagery taking satellites. And you may just recognize the image that's taken here, right? Looks like it was maybe taken sometime in the fall or the winter because there's not a lot of vegetation, but it's Falcon Stadium, right? In our example, let's assume that we have, essentially, you can kind of think about this as the area of your backyard, the width of it times the length of it. Well, we're instead of doing, feet or meters, we're going to use pixels as a way to describe the amount of real estate that our image covers. So in this case, let's assume it's 2048 pixels long by 2048 pixels wide. Let's then assume also that we have essentially the use of 4 bits per pixel. If you remember, the 8 bits per pixel was the best we could come up with as in that little example. The lady's face was in much, much higher resolution. We used more bits per pixel. Let's assume we're only using 4 bits per pixel, right? A 0, 1, 0, 1, whatever. 4 of the 0, 1 sets, then each of those is a bit. The math that I did there was I multiplied 2048 pixels by 2048 pixels. That gives us the number of pixels inside one image. And then if I want to find out how many bits are in each image, I just have to multiply by however many bits per pixel. And that gives us 160 million odd bits in an image. That's a lot of bits. That's a lot of bits. So now we actually have to talk about something really quickly. This is, let's see here. You are used to, I am used to anyway, your hard drive having, an amount of space listed that is in gigabytes or megabytes. And you see the uppercase B in the SI prefixes, meaning bytes, and the lowercase b meaning bit. So a bit is just a 1 or a 0. A byte is 8 of those 1s or 0s. So uppercase B, capitalized B means byte, so 8 bits. Lowercase b means just 1 bit. But there's also another way to describe it, and that's with gibbe and mebbe and kibbe bits. And instead of going 10 to the something, gibbe and mebbe and kibbe, fun to say, they do their data calculations with 2 to the somethings, right? So that's a binary way of calculating versus a base 10 version of calculating, which is what we're all used to, right? You go to Best Buy, you go to the store, and you want to buy a hard drive. It doesn't talk about gibbe bits. It doesn't talk about mebbe bits. It talks about gigabytes, kilobytes. Well, in this class, we're going to use bibbe. What I mean by that is kibbe, mebbe, and gibbe bits. So, for example, if I have a hard drive that holds 3 gigabits of information, I love saying it, that means I have 1 gigabit is, for example, 2 to the 30th. Sorry, 1 gigabyte is 2 to the 30th bytes. 1 gigabit is 2 to the 30th bits, difference just being that there are 8 bits in a byte. So let's assume that I'm designing the next worldview satellite, and I want to know, okay, well, if I buy a 3 gigabit hard drive from whichever contractor will give me a space qualified hard drive, how many images can I fit into this hard drive, and is this satellite going to work basically with its mission concept, or am I going to run out of space for all my pictures before I can download them to a ground station? Well, let's assume we have the image from before of Falcon Stadium that's 167 million-ish bits per image. The next thing we need to know then is, okay, 3 gigabits is the amount, 3 gigabytes, 3 GI uppercase B bytes is the amount of storage space I have. Well, if I was going to buy this hard drive and stuff it into my satellite, how much space is that in bits? So really this just becomes a unit conversion type of a deal. And so we're going to look at how many images that how many bits are in each image. And then now let's look at how big the hard drive is in terms of bits, not gigabytes. It doesn't do me much good because I already know the amount of bits in every image that I take. I want to know and compare that with similar units. How many bits can I stuff onto the hard drive? So if 1 gigabyte is 2 to the 30th bytes, and each byte is 8 bits, that means the total amount of storage on a 3 gigabyte hard drive, uppercase B, gigabyte, is 3 of gigabytes, right? 3 times 2 to the 30th, 3 of 2 to the 30th, 3 of those units stacked on top, times how many bits we have in a byte, which is 8. So that gives us almost 26 billion bits. 26 billion bits can fit on this hard drive almost. So then it's a simple matter of dividing 25.7-ish billion bits by how many bits are in each image, and that gives me that I can fit about 1,500, right? 1,536 images into a hard drive. That lets me do the necessary planning that I need to do for my satellite mission concept. Okay. Well, that's kind of an example problem of what you'll see, at least a visual representation of it. In the tutorial video that follows, we'll actually walk through kind of the nitty-gritty math that goes into doing one of those problems like you'd see on a GR. But it was a real pleasure to talk to you guys today because we talked about TT&C and the principles of signals, and we also talked about command and data handling, basically how much data can I store, how big is each of those data segments, etc. So this was great. Looking forward to talking to you guys next time. All right, guys, you know who it is. It's Major Cunningham. It's me. We're going to talk about my favorite actual topic in all of Astro 310, and definitely, well, just my favorite topic. I love RF. I love Wi-Fi. I love wireless transmission of information. It's just the coolest. That's what we're going to talk about here. We lump that under the command and data handling subsystem in Astro 310. Now, really, this falls under the telemetry, tracking, and commanding subsystem, the TT&C. This is how the rest of the world generally refers to this. We don't have a lesson devoted to that, although we could teach an entire course on radio frequency transmission, right, RF and SATCOM, and this is just kind of a real quick, brief overview. What we use for this is this monster of an equation called signal-to-noise ratio, S over N. In the business, it's often written SNR. But it's basically the strength of your signal compared to how strong the background noise is. So a good way to think about this is if you're sitting in church, for example, or a briefing, a quiet environment, and people are just kind of whispering and murmuring to each other, and then somebody out of the blue shouts, "I love astronautical engineering!" It's like you can actually hear that really well, right? Because the background noise is low and the signal is quite high. Now, in a crowded room, if your buddy's trying to look for you and find you and is shouting your name, he has to shout above the very high noise floor of all the people talking to each other, and it's likely that you won't hear him from across the room in a crowded room. So anyway, this is the same thing with signals trying to go to satellites and come back from satellites. The world is full of background RF radiation, and so to quote-unquote hear or to correctly receive a signal from a satellite or transmit one to a satellite, we have a lot of the same things to consider, like how strong is the background noise, how strong is the signal. We would like to have a signal noise greater than 1. In the real world, a signal noise of barely 1 isn't really actually sufficient. In Astro 310, it's going to be sufficient. SNR bigger than or equal to 1 is fine. That means that the signal is exactly at the strength of the noise floor. And again, in real life, that's not enough. You want SNRs in the 10 or higher range. I mean, that's one man's opinion. But it's better to be able to pick out the dude yelling about Astro in church, right, super loud, against the background of quiet murmurs, instead of the dude in the quiet room trying to get your attention, and he just sounds like he's part of the noise, right? The signal blends right in. So we want to know this ratio. It's important. We want it to be at least 1, but in real life, we want it to be much, much bigger. Okay, in any event, given the ground station in a satellite, command and data handling subsystem specifications provided below in this little table, we want to know the power of the transmitter. Power of X emitter is how it's abbreviated on your equation sheet. We're going to be in this upper right side of the back page, talking about communications. So PX emitter is what we want to know. SNR we're going to set to 1. It's the very lowest it can be, in theory, right, and still have a good connection. And this word here, actually, during the entire pass, these words I should say, that actually is significant. We're going to talk about that in a second. Okay, and it says the satellite has a circular orbit, which is great. That means it's not going to have an apogee and a perigee that we have to worry about. It has an altitude of 750. Good old altitude, right? Good old altitude. So let's see here. Let's write it here. 750. kilometers. Good. Okay, well, let's write out this whole equation. I'm going to rearrange it. I'm writing this big monster of an equation, but I like to rearrange it. P X-mitter gain of the X-mitter. We're going to talk about that in a second. I want to kind of walk through what all the terms mean. The Boltzmann's constant times bandwidth. We'll talk about that in a second. Times the gain of the receiver. The temperature. Over this term called free space loss. Now, this is not on your equation sheet. You know what? Let me just erase it. This term that's called free space loss is basically the loss of strength in the signal over distance. Signals get really weak over distance, right? That's why you can't somehow receive Wi-Fi from your house if you are at the academy, right? It's thousands of miles away. That signal is so weak as to be pretty much blending into the background radiation. So anyway, the free space loss term is wavelength over 4 pi r squared. All right, let's start off with r. So let me draw my Earth here. Here's my little satellite dish. When the satellite is directly overhead, it's funny because the radius, the r that we use is, this is, depending on how you want to think about this, this isn't really the orbital radius. Not depending on how you want to think about it. It's just not. It's not. We use r in this equation, but it doesn't mean the same r. The distance of the signal between the little ground station transmitter and the satellite, that's how r is being represented here. Again, don't like that. Don't like it because what we've been saying to you guys so far is that r is from the middle of the Earth out to the satellite. It's a position. It's the magnitude position vector. Not so in this case. In this case, r is just the distance between the satellite and the transmitter, having nothing to do with the radius of the Earth. Now, let's imagine the satellite's orbital path is a lot like this. It's moving this direction. If the ground station looks out over the horizon, as soon as the satellite, we call it rise, satellite rise, as soon as the satellite rises over the horizon, would you buy that this r is much, much bigger than that r? We're going to call that r max. Because as the satellite flies over the ground station, it gets much, much closer to the point where it's directly overhead. That's the shortest r. That's the best case scenario. But our problem says we want to guarantee good connections for the entire pass. So that means SNR has to be above 1 for the entire pass. So that means I can't plan for just this little r worth of free space loss. I have to actually plan for, whoa, r max worth of free space loss. As the satellite gets closer, the signal gets stronger. That's great. But I have to at least be able to talk to the satellite all the way out at r max. And of course, as the satellite sets, yep, we talk about it like the moon and the sun. As the satellite sets, it will be at a distance of r max again, right before it drops below the horizon and you lose contact with it. Okay. So that's r. Here's how we calculate this r. We want to use r max as this r, for the sole reason that, again, we have to plan for the worst case scenario. We're making pretend like we're engineers in Astro 310, right? We're trying to think through an engineering mindset. So R max, our equation sheet tells us the way that we find this very long R max distance is like so. Take the radius of the Earth plus the height of the orbit, we square that, and then we subtract the radius of the Earth and square that. So a little plug and a little chug. Let's see what we get. 8.137 plus 750 squared minus 78.137 squared equals good. So I get this is 3182.72 kilometers. 720 if you want, because I'm carrying 3 sig figs at least. It's what I do. It's what I do. All right, so that's the R, the distance between the transmitter and the receiver. Again, I don't like the fact that it has R, and you guys are used to R being something totally different. I can tell you this confuses folks. So be not confused. Be not confused, my friends, my students. Be not confused and use RMAX properly here. Okay. All right, wavelength. Let's talk about wavelength. So as you guys saw, we have a signal, the distance between successive crossings of the axis this way, and my wave is not great, but basically the distance between a rise and a set like that in a, what would you call it, in a perfect sine wave. That's our wavelength. And radio frequency signals have wavelengths too, and frequencies. So you guys might remember all the way back from your physics class that the speed of light, if we're dealing with an electromagnetic wave, is the wavelength of that times the frequency of that. And they all travel at c. c is our speed of light, which we typically round up for courses like these to 3 times 10 to the 8 meters per second. Okay. My equation uses wavelength, but I'm only given frequency right here. So let's first of all solve for, let me solve for wavelength in the abstract, and then we can plug and show. Frequency is the number of full oscillations in a second. So frequency is number of oscillations per second, and the oscillations kind of becomes unitless. It's like, yeah, it's essentially unitless. So a hertz is a once per second. So how many once per seconds do we have in a second? Well, we have 3 times 10 to the 9 oscillations per second. So this is a 3 gigahertz wave, actually. 3 times 10 to the 9 hertz. So you can almost do that in your head. That becomes 0.1, and the units are meters. So good. So that's the wavelength that's going to go in here in your free space loss term. There you go. Okay. Now let's move over to this next, or the first huge term here. Power of the transmitter is something that's pretty straightforward. That's what we're actually looking for, but it's the amount of juice that the transmitter is putting out a signal at. So let's talk about gain. G stands for gain. And again, we could have entire classes on what gain really is, but think of it this way. A little antenna reflects a lot of radiation back out. Or if it's coming in, it reflects a lot of radiation, right? A big antenna reflects a ton of radiation. Or if it's going the other way, right, it focuses a ton of radiation. I'm trying to be too fastidious with my arrows here, but basically bigger antennas have more gain. And you can imagine that on the Earth we can build massive antennas. And the most extreme example of these are some of the NASA's Deep Space Telescope antennas. They are mind-blowingly huge. But on a satellite, you often don't have that kind of real estate to use because you've got to launch all that into orbit. So what I mean by that is if you're trying to put an antenna on a satellite, a communications antenna, it's not going to be very big. It certainly can't be too much bigger than it can fit in a payload fairing, in a payload, basically in the container of a booster to get to space. So all that to say, satellite antennas are going to relatively have a much smaller gain, generally speaking, than ground transmitter antennas. But that's what gain is. It's basically the ability to focus RF energy. So for example, your iPhone or your Samsung or whatever you have, because, well, this gets a little bit of antenna theory, so I'll wave off, I'll let that part go. But essentially lower gains like your cell phone are antennas that basically are almost omnidirectional, which means you could point your cell phone any which direction, right? You can lay on your bed and be talking to your parents. You can be doing a handstand and talk to your parents. The orientation of the cell phone doesn't actually really matter, as opposed to big dish antennas like you might see for Dish TV or Direct TV, on the outside of your house. Those signals are coming from outer space. They need to be focused more, so the gain of a dish antenna, it's actually shaped like a bowl, so it can focus the radiation, that gain is higher. So both basically shape and size play a role in gain. And I just let that go because I tell you that because gain is a very confusing concept if it's not part of your daily life. Okay, K is Boltzmann's constant. We're still good with that. B is bandwidth. That's essentially if you have, power versus frequency. And you've got all these kinds of signals, on a spectrum analyzer. Basically, bandwidth is the portion of the spectrum that you get to use. So it's a chunk. It's a chunk of spectrum, a chunk of the EM spectrum. Okay. Last thing is temperature. We want to know what the actual temperature of the receiver is. And that's just literally the ambient temperature. How warm is that piece of material that's focusing the signal? How warm is the antenna? Okay. So I ran out of space explaining it, so I'll move on to my graph paper, my extra scratch graph paper here. I'm going to rewrite the equation now that we've talked about all the terms. P X emitter, G X emitter, transmitter is what X emitter stands for, gain of receiver, K, B, T, times our free space loss term. Remember, R is not talking about from the center of the Earth, it's just really talking about the distance between transmitter and receiver, and that power is squared. Okay, first things first, we already know what we want our signal to noise to be. We want our signal to noise to be 1, or greater, much greater if we could, but at least 1. So we need to solve for power of transmitter, because that's what the problem wants us to know. Like, how juicy does this signal have to be? How much oomph does it have to get? How much oomph does it have to get to the receiver? So there we go. So let's solve this in the abstract. All right. This is kind of a beast, but we can do this. Alright. Now let's plug and chug. We have to be a little bit fastidious because we want all of our units to be in SI units. So that means we're not going to accept kilometers, we need it in meters. We're not going to accept megahertz. Here, I'll pull this back down. We're not going to accept megahertz, we want it in hertz. We're not going to accept Celsius, we want it in Kelvin. We're not going to accept, let's see, yeah, that's the big ones. So signal noise, we're told we want 1 or greater. K on your equation sheet is 1.381 times 10 to the negative 23rd. Bandwidth, we were told was 1.5 megahertz, so that's 1.5 times 10 to the 6th hertz. Temperature we want in kelvins. We're told that the receiver temperature is 20 degrees Celsius. That means we got to add 273.15 to get it into kelvins. We need it in kelvins. Gain is a unitless equation. It's usually actually measured in decibels out in the real world, but for our purposes, it's a unitless base 10 unit. So the gain of the transmitter, we're told, is 7. The gain of the receiver, we're told, is 14. We're going to use our speed of light over frequency that we're told, just like before. Remember, we found over on the previous sheet that was going to be 0.1 meters for the wavelength over 4 pi R max. Let's see, R max we found in kilometers, but we want it in meters. So 3182720. So there you go. There you go. I'm going to put commas in there. And we square that. Right. Let's manage this monster. We can do this. Okay. Divide by 1 divided by 4 pi. And I stored that R value in the calculator. Squared. Whew! So this is a little bit of calculator management too. Get to know your calculator and how you can use it, store values and stuff like that. Not before the GR, but during the GR. Okay, so I get this is 9.912 watts. That's how juicy the transmitter has to be. And I say that in a silly way, but basically how much power does the transmitter have to put out to reach the receiver, have its signal still be above the noise floor? It needs to be right about 10 watts there. Ah, that's a good one. Okay, let's go back to the original sheet. I'll look over there. Okay. Okay, so that's kind of the RF, what we call signal to noise part of this equation. I shouldn't say signal to noise part of the equation. Signal to noise part of the concept of the course. Now, break. Now let's talk about the data transmission part, which is to say, what are your data speeds? You do this kind of calculus all the time in your brain when you are dealing with low internet speeds, especially when you're dealing with fast internet speeds, when you're trying to stream Netflix, HD versus standard definition. You guys you don't even know, but you do these kinds of calculations in your head. So let it just be that intuitive if you're able. So, okay, so the camera on a satellite is capable of taking images that are so many pixels by so many pixels in a certain color scheme that gives it basically a certain size of bits per pixel. So if the satellite can transmit data at a certain data rate, how many images can be downloaded if you get 5 minutes of good contact with the satellite? So let's go over a couple things first. Evidently, this satellite is taking really skinny pictures, and this is not uncommon. But are like 1024 by 16384 pixels. And if you guys, this is a terrible drawing of pixels, but each little picture element or pixel is a little tiny square. It's like if you get your face close enough to your computer, you can see that the image is actually made up of tiny squares. Each tiny square is a pixel. So the problem is telling us that this satellite takes pretty high resolution pictures that are very skinny, right? They're kind of rectangular, very rectangular. So that means each picture has a certain amount of pixels. So let's see, one pic equals, the area basically in pixels. 16384 times 1024. One 16 pixels in an image. Okay. So how big is that data-wise, like hard drive-wise, or Wi-Fi speeds-wise? How big is pixels in an image? Well, it depends on how big each pixel is. So if one pic is this huge number of pixels, pixels per image. And there are 8 bits in every pixel. That means you have 1, 3, 4, 2, 1, 7, 17, 8 bits per image. Pretty high-res photos. So they're 134 megabytes per, or megabits per picture. Anyway, or per image. Sorry, I'm saying image and pic is the same thing. The satellite can transmit data at a rate of 20 megabits. Okay, a megabit is on your equation sheet. You guys are used to hearing, and I'm more used to hearing mega as a prefix, right? Mega is times 10 to the something. So mega is times 10 to the 6th. Mebe is 2 times 10, or sorry, 2 to the 20th. Blah, blah. So mega, if your hard drive is so many megabytes big, or you have so many megabytes of RAM, that means you have 2 times, or sorry, blah, blah. You have something times 10 to the 6th. Let's say your hard drive has, let me try and tie the bow on this. If your hard drive has 30 megabytes of space, that means it has 30 times 10 to the 6th bytes of space. And there's 8 bits in a byte. Okay, so you can figure out how many bits are on your hard drive. Mebe is, instead of times 10 to the something, mebe is 2 to the 20th. So I guess what I mean by that is 20 megabits is 20 times 2 to the 20th bits. So that's 20 times 2 to the 20th is 2971520 bits. Now that's just a number of bits. The problem tells us that if we're transmitting data at a rate of that many megabits per second, we write it like that, 20 mibs. Put P in there, mibs. That translates out to 2 million odd bits per second. 20 million bits per second, yeah. Okay, so we've got how big each image is in bits, how fast we can transmit bits in a second. So that means during a 5-minute pass, I want to know how many seconds I have. 5 minutes times 60 seconds a minute gives us 300 seconds that we have. Okay. So let's see here. In a, running out of space. In a pass, we'll go up here. In an overflight, basically, it's 300 seconds. If I transmit this many bits per second, bits. 1 second. So if I have 300 seconds to transmit every pass, and I'm transmitting at 20 million odd bits per second, that means during one pass I can do 629145600 bits per pass. Almost there. Give this up a little more space down here. So the question is, how many images can we download per pass? So if I know that I can transmit that many bits in a pass, and each of my pictures is that many millions of bits, millions of bits, then all we have to do is divide 629145600 bits per pass by how big each image is. 21728 bits per image, and when we divide like this, the bits cancel out and the image comes on top. So essentially what you have is 1, 2, awesome. This gives us 46.875 images for every pass. How many whole images could we transmit? That's kind of another question. The number of whole images, like that are complete, you can see that I have, a little bit left over. So I could transmit 8.875 worth of the next image. But as far as whole images go, I can really transmit 46 images. Whole images, right? Both are correct. Okay, cool. Now. Problem 3 says, okay, if all that stuff from problem 2 is still true, let's say the satellite has a hard drive on board. It has one of its own hard drive. It has a data storage capability of 1 gigabyte, right? So a gigabyte would be 1 times 2 to the 30th, right here, 2 to the 30th, bytes. And of course, we're going to multiply that by 8 because there are 8 bits in a byte. So let's see how big the hard drive space is. 1 gigabyte equals 1 times 2 to the 30th bytes. That is 10737418824. Feel free to just kind of use scientific notation on that if you want. I like to keep all the digits, but don't let that stop you. So that's the amount of bytes. And it equals, if we multiply that by 8, here I'll just do it on the calculator. It gives us 8.5899345592. Oops, don't know why I put it. Stop. Bits. So our entire hard drive, if you want to think about it this way, can hold basically 8.58 times 10 to the that many bits. And it says that it gives us that each image is 134,217,728 bits. Oh, that's kind of nice to know. We found that. We confirmed that. So basically, how many little images can I store in my hard drive? Not that they're stored like this, but basically how many can I store before I run out of hard drive space? Well, if I can store 8.58 times 10 to the 9th bits per hard drive, divide that by how big one image is, which is 134,217,728 bits per image. Again, because we're dividing, the bits cancel out, the image comes on top, and this becomes, let's see, I can store exactly 64 images in this hard drive. Woo! All right, so to recap, we talked about RF data transmission, right? Signal strength, that's signal to noise ratio, signal strength. Then we moved on to talking about basically data transmission speeds, and then hard drive sizes. So there's a lot that goes into talking about, obviously, a satellite's command and data handling subsystem, but these are some of the big considerations. And again, technically we would call this a telemetry and tracking and control subsystem out in the real world, but basically the onboard computer and all of its equipment to talk to the ground is the CDHS. So hope that was helpful. We'll talk to you guys next time.